Can I have everybody's attention? We're about to get started here. This is actually the first seminar in our spring 2010 Space Science and Physics lecture series. And this week we're lucky enough to have Dr. Jim Clarage. And I could tell you a little bit about him, more than you see on the abstract or in the announcement. Dr. Clarage here, he started off, before he became an assistant professor of physics at University of St. Thomas, he was an adjunct professor here at University of Houston, Clear Lake. And before that, he also worked at the University of Houston Central Campus, where he taught a little bit and he did some web development work. And so he's got this huge background which spans from doing physics, doing some things with biophysics or biology, doing other things in art. So he's one of these most well-rounded people that you're going to see in this series. And today he's going to give a lecture about the laws of physics and are they really fine-tuned. And so this should be a very interesting talk, as all of his talks are, and we're just very lucky to have him today. So,
okay,
thank you. Jim?
Are you recording there?
Yep.
Do you know the radius of how far I can walk? Or,
you can go pretty far.
Okay, good. All right, there's an uncertainty principle here then. If David claims I have a certain breadth, that leads me to my first caveat, is that means I'm not an expert on this subject. I'm not an expert on any subject if I have that breadth by the uncertainty principle. So if there's anyone I have to scan here, I asked David what the audience would consist of. He said, well, it'd be about half Nobel Prize winners and half Fields Medal. But seriously, if anyone is an expert on fine-tuning, I guess definitely interrupt me and interject into dialogue, but I'll be first to lay down and admit, okay, this is an area that's interesting to me as a scientist, and it's one that I'm looking into and I would love to give a talk on, and that's why I'm giving a talk on it. The other is I'm from the University of St. Thomas, that's up in Houston, and it's an undergraduate institution, liberal arts college. It's small. They do have a doctoral program though, but they only give one doctoral degree, and that's in philosophy. So about half the campus is philosophy. It's very philosophically dominated. So I don't know if has anyone been to a philosophy talk as opposed to a science talk? Okay. I was horrified the first time I did it, because what it is someone takes a paper and they read you their paper. And you have to somehow keep track of someone reading paragraphs of logic through a paper. So that's a style that we are often asked to employ up there. The science talk is to have slides and equations. I'm going to have to do both in the nature of this material. So I apologize if it gets to a state where I'm reading here. That's the side that's kind of digressed to the philosophy maybe that I'm in. Now you could just throw something at me if you crumple up something. Okay, so to go with that, I can start off. And when I start, has anyone heard of the notion that somehow the constants of nature, for instance, the constant that describes how strong the gravitational force is, that somehow fine-tuned to be just the value it is so that we get life, an intelligent life to evolve? Did I just see these? Okay. So that's good. Many of you have heard of this notion. How many, just so I get a feeling, have taken a physics course before? Oh my goodness. Okay. This is great. Excuse me?
Many years ago.
Okay, many years ago. Well, okay, that's good. The idea is many of the constants are tuned. So just as a reminder, this constant G stands for the gravitational force. One way to write that is in a Newton form. If I have two masses, m1 over m2, and they're separated by some distance, there'll be a gravitational force. And I'm sure we've all seen that. This constant G is important because that tells you, well, how strong is that force? And if G were much stronger than it is, the idea is everything would fall much faster. Stars would be much denser, and nuclear reactions would go much faster. There's some claim that you couldn't get a nice stable solar system, and you couldn't get life to evolve if that G value were too high. Now, I'm not going to go through every argument. If this were a purely scientific talk, I apologize if you came for that. I'm not going to go through and work through either Newton's or Einstein's equations to show you if G is different by a certain amount, you don't get complex amino acids forming the free energy. It's not going to be at that level. I honestly can't do it at that level. I've read on that level. So some of these I'm just going to go through in words as a review. But the gravity one is one. Also, it would have affected the rate that the Big Bang happened. If G was too strong, the bang would have happened and would have already collapsed by now, meaning we would not be in this room to talk about it. So that's interesting. And of course, G is too small, then there's essentially no force of gravity, and you couldn't get a planet together to have life happen. So, for instance, here's a claim. The New Scientist magazine had an article, and someone at school showed me this, someone on campus showed me this, and I was impressed. These are just quotes out of here. It was a whole article on the strangest force, gravity. And one of the strange things they said is, why is gravity fine-tuned? And the article said that to 1 part in 10 to the 15th, that value of G has to be exactly the G. Now, if you had I was a little puzzled, thinking, that just doesn't seem right. And I read the article trying to say, where do you get that 10 to the 15th? And I couldn't find it in the article because it's a New Scientist article. But that's fine. This is an example of the claims you might see. Here's another good example, and this one I actually really do like. And this is if we look at the masses of the proton and the neutron. So those, again, are constants in nature, and I'm giving you their value. In case you couldn't remember them, these are the value that's in the back of a physics textbook, and as you can see, the neutron is just a little bit heavier than the proton. And it's in the 4th decimal point. So we might say that's to 1 part in 10 to the 4th, because it's in the 10th decimal place. The 4th decimal place. Now this is an interesting one. Let me draw here kind of a pseudo graph here, where I'll put the mass, or by E equals mc squared, that's the energy, whatever, of these particles, a proton and a neutron. This is saying neutrons up here, and protons just a little bit below it. So neutron and proton, of course neutron has no charge on it, proton positive charge. There's a very small difference, and you can look at different cases here. Let's just explore. Let's say, is that just a coincidence, good or bad that they're close? Let's look and let's assume, what if the mass of the proton were greater than the mass of the neutron? What would happen? Turns out that would be catastrophic. If I have a free neutron is at a higher energy. Things want to get to a lower energy, even in high energy physics. A neutron will decay, and it will decay into a proton and an electron. So you start with 0 charge, and you end with 0 charge. So it's a nice, beautiful reaction. If there's any chemists, it's like a chemical reaction. So that's the state of affairs, and that really happens. That's the weak nuclear force. It's beta decay. Now look at what happens here. Let's say the proton mass were greater than the neutron mass. Even just by a little bit, but whatever it is. If I have neutron down here, this is a problem. This as a free neutron would eventually just decay, free proton would eventually just decay into a neutron. Okay, so what? So what? You wouldn't have atoms. You'd have a universe full of neutrons. What are the electrons going to do? You can't even imagine how you would build an atom. Because eventually you just have neutrons, and the electrons, they wouldn't want to go around them. So it's very hard to imagine getting even an atom. Now obviously if you can't get an atom, you can't get chemistry or biology or any of this sort of stuff. All right, let's look at another case. Let's say the proton is less massive, but let's say that mass difference is tiny. Let's say the mass difference is huge between neutron and proton. So proton's much less massive than neutron. These details I won't go into, but you can show that deuteron then would become unstable. Deuteron just means it's that state of having a proton and a neutron together. You need that bound state in a star in order to drive what's called the PP reaction. In other words, you couldn't have stellar physics happen. You couldn't have stars burning fuel and changing hydrogen into helium, because a critical state in that reaction is to have a deuteron. So let's say, well, what if mass of proton and mass of neutron were very, very close to each other? Almost equal. So that the protons couldn't decay into neutrons, and you kind of just had protons and neutrons, but they're about the same energy level. That's a problem because then no beta decay is possible. Remember that first reaction I showed you, a neutron can decay into a proton and electron? The only reason it can do that is there's enough energy left over to give you another little electron coming out. So beta decay would be impossible. That's a problem because, again, it would mess up stellar physics and the whole weak force. So this is an interesting case. It's a good example. It's just using constants in nature, these two constants, mass of proton and mass of neutron. Or it seems like that value, they can't be too big, they can't be too small, has to be just this right mass difference, which is about that of an electron. This is just an example of that reaction that you couldn't happen in a star, meaning you couldn't have protons fusing together to give you what you want, which is helium in a star. The whole function of a star would be lost. And of course you need helium, because when you get three heliums, they come together to make carbon, and we all like carbon, right? We all know carbon's a good thing, being biological creatures. All right, there's many examples of the fine-tuning. Those are the two I'm going to go through in detail before I move on to some critiques here. Unfortunately, this line of reasoning, once we accept it, leads to a problem. Well, I call it a problem. It has implications. We're going to say things are fine-tuned in some way. We're going to say they're fine-tuned. You have to kind of ask, well, tuned for what? Well, we assume for life they're tuned. Intelligent life is usually how it's phrased. That's called the anthropic principle. As if there's this extra principle of nature. The constants couldn't be anything they wanted. They also had to produce complex life or intelligent life. That's called the anthros is a Greek word for man, like the word Andy. Anthros, it's a principle. Now this then is problematic. Let's say you accept the anthropic principle. Then you have to ask, well, if I have tuning happening, that's a verb, to tune. What's the subject? Who tunes? In science we talk very objectively. The experiment was done by the constant of G was measured, is what we say. It's done with the passive voice. So here we say the laws of physics or the constants are tuned. That's a passive voice. What's the subject? So that's problematic because you've got to talk about a tuner then. And so science is entering something which you don't usually want to associate science doing. Now there's a way around this, and that's called the multiverse, which you may have heard of. Yes, it may appear that our universe is tuned, but that's just because we're one universe in a whole multiverse of other universes, and we just happen to be here in this one. And that gets rid of having to do a designer if there's just a bunch of different universes. Okay. Let's go through. These are two ways of stating the anthropic principle. I'm just going to go through these briefly. The anthropic, the design, and the multiverse. These are due to Brandon Carter, but they've been around for quite a bit, this anthropic reasoning. This is the weak form of it. I think during talks people can read faster than a presenter can speak. So I'll just let you read through these. But they're in two forms. A weak form, which doesn't kind of make a scientist cringe too much. It's sort of the obvious form. Strong form does make a scientist cringe. It kind of gives a purpose that the universe must be such as to admit the creation of observers at some stage. That's kind of saying there's an intent here. It's a strong statement. Notice the word observers, though, shows up in weak or strong. We're not just saying we could create ants. The universe isn't tuned to create anything. This model or this principle it's tuned for observers. Okay. Now, I guess there was another caveat I should have mentioned. I'm at the University of St. Thomas now, and it has the word saint in the word of it. Part of the reason I got interested in this, don't worry that this is a person coming to proselytize. It's actually just the opposite. This reasoning happens a lot in theological and philosophical circles, and I find a lot of problems with the anthropic reasoning and the fine-tuning reasoning. That's the purpose of the talk. Just in case you're wondering, sitting there. Okay, there was actually a prediction, though, based on this anthropic principle, and some of you may have heard of this. Hoyle, who was an atheist at the time, was realizing he was trying to do the stellar nucleosynthesis. So you start with hydrogen, and that fuses to helium. All right, 3 heliums then fuse in together, and you can just count up the numbers there, and that gives you 12 things. That's the carbon. 6 protons, 6. So that's how you get carbon. Hoyle tried to work through, let me work through the physics. If I get 3 heliums coming together, what's the probability in a star at that temperature that they'll make carbon? And you get a horribly small reaction rate. It just shouldn't happen unless carbon has a resonant state at this energy, this predicted energy. And so Hoyle, and it's just the energy that you would expect them to come together in the temperature of the star. Now at the time, carbon was not known to have this energy level. The carbon nucleus. I'm talking about nuclear energy levels, not the atomic energy levels. So Hoyle essentially predicted from this principle, carbon must have a resonant state of the nucleus, which makes this reaction happen faster. Now what do I mean by resonant, just as I had to bring some little props here. Resonance means something happens at the natural rate. For instance, on this slinky, it has some resonant frequency. If I try to work the frequency too low, nothing interesting happens. If I work it too fast, well, it's kind of interesting. But if I work this right at the resonant frequency, I get huge effects happening. That was the only thing, if there could be a resonance in the nucleus of the 3 heliums, which could get carbon. So Hoyle predicts this. Literally a few months later, out in California, he had some people hear about the prediction, and they measured a resonant rate in the nucleus of that energy. So this was, probably it's the only case that ever happened, but unfortunately it made the anthropic principle important. An example of making a prediction something should happen, otherwise you don't get carbon and you don't get life. All right, now when Hoyle discovered this, he called this a put-up job. Denature, oh yeah.
How does that support the anthropic principle? Other than it allows an easier way of getting carbon, which allows most of this.
Well, because he used that as the starting point, apparently. If I start with the assumption that the universe's laws and constants all must lead towards making an intelligent person, which he then said was carbon. That was the proxy carbon.
Carbon-based.
The only way you can get, carbon-based life. The only way you can get carbon is if there is a 7.65 MeV level in the nucleus. So he predicted there has to be this level in the nucleus, and then they go out and measure the level, and lo and behold, they find it. I'm not saying I agree with that then tells you, oh my gosh, there's an anthropic principle. I'm saying, though, this is given by people who do anthropic reasoning of one of the first instances.
If the resonance was off, wouldn't we just have to wait for the universe to get older to accumulate the carbon to make us maybe?
Yeah.
Okay, so it'd still maybe be here, just be older universe.
All right, I should just move ahead to the. I'm with you. There's lots of alternative scenarios that you can develop here. So I think I should move right into this. Is a good segue. You're already thinking ahead, going, hey, I can see some critiques here of my own. I've got gobs of critiques. I've got folders, literally folders and things. I only have a certain time. I'll just go through as many as I can go through. And if you can't hold yours back, we can all add them. Let me just say one. I skipped, that's anthropic, and let me give, designer then comes up, and Stephen Weinberg, I just have to read this good quote. He was asked by the New York Times to write some article on the anthropic principle, whether he thought that meant there was a designer, and he has this funny quote. He says, even if a universe were completely chaotic, without any laws or regularities, it still could have been designed by an idiot. So I think it's just a great little, just like that. Okay. And then let me go through, instead of giving these critiques numbers was getting a little dry when I was doing the PowerPoint. I've instead just given them labels from the area of study. For instance, literature. When I hear all these ideas about a multiverse and anthropic principle, and I didn't go through multiverse. Multiverse is just a way of saying if you don't want to think this universe is the only one and it apparently was designed for us. The idea is, well, there isn't just a universe. There are an incredible number of universes, and that's why it's called multiverse. And this is very schematic, and you may have heard of these. So every circle is a universe. We live in one little tiny section here, or maybe light could have traveled to some Hubble radius. And all the constants of nature we experience are in here, and they have their values. Mass of proton, mass of neutron. But somewhere else, in another part of the multiverse, the mass of the proton, mass of the neutron are different. G is different. These universes may just die out. They may never make carbon. So the multiverse is the idea. There's many of them. This is very big in string theory and in physics today. That's a way of saying, no, it wasn't designed for us. There's just anything you can think of. There's all possible worlds. Now, when I hear this multiverse and all possible worlds, I can't help but think, has anyone read Voltaire's Candide? Or you were forced to read it maybe? Okay. This whole story is a farce built upon the notion that it makes sense to talk about possible worlds. It's a famous novel from 1759. It was written in a response. There was a philosophical movement with Leibniz, with the calculus and the infinite coming about. Leibniz would talk about all possible worlds, and you could reason that ours was the best, and everything was arranged. For instance, the reason you have a nose, this is in Candide. Professor Pangloss says the reason you have a nose was God knew that you would have to wear glasses, and that's why the nose was put there. And so everything's designed perfectly. And this sort of reasoning is the reasoning of all possible worlds. The last sentence goes through this. Anyway, it's a fun story to read. If you read the last paragraph, it's imagining if all, not the constants of nature, but all the constants in their environment. If the garden were a little different, if the woman across the street looked a little different, if all these things were the case, then you would not be able to sit here and enjoy your citron and your pistachios. That's what makes life good, that it is all tuned this way. And the funny character in here is the Leibniz character, the philosopher or the scientist. And that's Professor Pangloss is his name. And this, I didn't make this up as a joke. This is in Candide, the title of this person who invents this multiverse or these all possible worlds. And I can't even say this, the metaphysical theogeo cosmologico, which when I read about multiverses, I kind of think, yeah, that sounds like the position title you probably have. I also say if anyone does multiverse research here, I take everything back that I'm saying on the... Because there are interesting things that come out. So here's another thing, is we can look at history. This is not reasoning that has just come up since 1958 with Hoyle, or with Carter in 74, the Anthropic Principle. This has been used over and over in history, this idea that there's a tuning going on. And so there's a long history of this. One is when Priestley, in 1774, so right before the revolution here, Priestley discovers oxygen. It was a great discovery. We take it for granted now knowing there was oxygen. And at the time then, they could measure the concentration of oxygen, and it was realized, my goodness, this is amazing. If we would have had less oxygen or too much, if you have too much, you get asphyxiated. Isn't it amazing? Our Earth is designed with just the right proportion, not too much, not too little. That a being would do that for us. Now, of course, we know the oxygen did come from a being. The oxygen came from the cyanobacteria that lived on the early Earth. The planet didn't start out with oxygen. The planet started out with a lot of CO2, horrible CO2 levels. And cyanobacteria kind of took over and did their own way of destroying the atmosphere, which we took advantage of breathing. There's another history. We can just step through history, different characters that argued from the structure of plants is what this was, getting towards the 1800s. Let's see. Was this Henderson? No, there was another one, Henderson, who looked at the energy levels in atoms. And they're set, and they're set in just a nice hierarchy, a nice harmonic hierarchy, so that you can get chemical bonding, so that you can get carbon-carbon bonds, carbon-hydrogen bonds. This was a great argument for some amazing tuning happening in the levels. Of course, this was explained then, Linus Pauling, once you have quantum mechanics and group theory, there's another explanation for why it follows this nice harmonic sequence, and that was, this is one of the most famous papers, at least to chemists, is Linus Pauling's. He explained the chemical bond in terms of quantum mechanics. If you've taken a physics course, and I remember my physicists, I'm sure David says this in his courses, they go, well, chemistry is just applied quantum mechanics. And that was kind of due to Pauling. Pauling showed, he did a lot more that was interesting. Physicists thought in the basis set of S and P orbitals. So say at the 2 level, n equals 2 level, you'd have 2s and then 3 2p's. Pauling's genius was to say you can take linear combinations and change and get a whole new basis of 4, and those are the hybrid orbitals, the sp3. Once you realize that nature can take advantage of those other superpositions That gives you the chemical bond. The sp3, you get 4 things. That gives you all the bonding properties that carbon needs. Okay. There's been this phrase, not too hot, not too cold, not too this, not too that. The mass of the proton, not too heavy, not too light. This all was dubbed in 1935 the Goldilocks planet. And it's a very catchy phrase. And I have to admit, when I was growing up, my parents used to tell me about this kind of in a fable way. We were on a Goldilocks planet. You have to, of course, know the Goldilocks story for this to really make sense. But there was that story with the porridge, just to take one example. 3 things of porridge Goldilocks goes upon. One's too hot, one's too cold, one's just right. And so Goldilocks eats that porridge. That's the model of Earth. We have all these planets around the sun. And here's a good question. In 1935, how many did we know of? When was Pluto? Yeah, so we would have had all 9. So you have these 9 planets. Only one of them appeared to have life then, or appears to have life. And of course it made perfect sense, because it was not too hot, not too cold. If you're going to be on Mercury, that's too hot. Goldilocks doesn't want that. You don't want to be on Mercury, that's too cold. We seem to be just at this perfect spot, and there's a lot of reasoning that went on with the Goldilocks planet about how perfect that spot was. And that led to a characterization which led all the way up till the 60s of what life required. Now this is what it required. You had to have it. It was not negotiable. It had to be not too hot or not too cold. And there's a temperature range pretty much around what you would want to live. It has to have oxygen. That's one. Had to have some oxygen, and you have to have sunlight. All right. So that's one reason you couldn't have Pluto. There's just not enough sunlight on Pluto. This went, and this has different phrases, also called the privileged planet, the Goldilocks planet. There's people on campus who try to sell me this DVD still when I walk around the campus. It's actually interesting to watch because it does let you realize all the interesting parameters that happen. But then in the 60s, and many people don't even know about this, there was a life form discovered. And this is a little long, but this is an undersea hydrothermal vent. And these are at the fault lines right on the plate tectonic lines. Ring of Fire is a place on it. So you have to believe in plate tectonics and that you can send ships down this far to measure this. But it's these hydrothermal vents, and this is how the continents move. And when they do, there's these horrible acidic temperatures, high temperatures way down in the ocean. The temperatures here are above boiling. It really is just steam and boiling coming out. The pressures are horrible. There's not much oxygen, if at all. And guess what? There's bacteria that thrive there. Okay. I remember being shocked when I heard this. I'm still amazed that you get bacteria down here. These bacteria are thermophilic bacteria, meaning they love heat, thermophiles. They can live 118 degrees, and there's even evidence up to 140 degrees C, 140 degrees Celsius. Water boils at 100 degrees. Right? This is thought, up until these were discovered, that was absurd to think that you could have this life form. So let's revisit this. The not too cold, not too cold is right out the window. You can have incredibly hot. Oxygen is not a requirement. You can have living organisms that are anaerobic. They can do a whole different metabolism. It's called anaerobic metabolism. They don't need sunlight. This is huge. All they need is heat, and then these need sulfur. That's all they need. Now this is big if you think about it. And maybe you have. I'm getting excited because I still just love these little critters that they can do this. This means you don't need stars as a sunlight source to make living things. Now, some of you realize, yes, but you need the stars for other things, to get heavy elements. Okay, that's fine. But this, at least at this level, you've taken away a whole swath of tuning. You don't even need your tuning to give you stars as a source of energy and metabolism. All you need is heat, meaning technically all you need is a thermal gradient, if you want to think about it. And this is a joke, actually. There's one of my colleagues is a priest there, and he's the oldest physicist, and he doesn't like any of the tuning things either. He said, he'll go on and say, God's not a boundary condition, he's not an initial condition, God is love, so stop worrying, But a physicist wants to make it out as something else besides love. So his point, here's a joke that goes on this, is why Why is hell, why do you know that hell is isothermal? Isothermal just means the same temperature. So would it be possible to go to a part of hell that's colder or warmer? But no, hell has to be isothermal. Why? Has anyone heard this too?
No engineers have that.
That's right. And can you explain why does that? Yeah, there's no engineers because an engineer could do what? Yeah, they could find a way to harness that temperature gradient to build a refrigerator or something. That's what these critters are doing. You give biology and Darwin a gradient of temperature, and it will find a way to make life. Okay. Now here's another. Oh, in case you're wondering how they do this, these little bacteria, it's not a trivial thing. If you fry an egg, what you're doing when you're frying an egg is you're destroying the proteins. When you get the proteins too hot, they denature. Proteins are these beautiful, you get a polypeptide that folds up to just the perfect shape. This is an example of a polypeptide formed into a perfect shape. That shape will denature at even 80 degrees C. If I throw you or a frog into some hot water, you will denature and die, and an egg will fry. And you can't go backwards in this. It's irreversible. It's used as an example of the arrow in physics all the time, this frying an egg. Biology got around this, though. It builds this disulfide bridge, it's called. This is an amino acid called cysteine. And what happened is evolution, the thermophiles, however it happened, built into this little secure disulfide bonds. They're covalent bonds, very strong, so that even when it gets very hot, the protein can't break apart because it's got these cables of disulfide. This is an example. Biologists did not know this until they studied how are the proteins not denaturing? How are they not denaturing? And they found when they solved the structure was because they have these extra cables in here called disulfide bonds. Okay. It gets even better, and I actually only learned about this one last year, but I bet this room full of people has known this story just by where you live and where many of you work. There was of course, organisms got up on our moon missions, and there was a camera sent up on Surveyor apparently in 67, and then when Apollo 12 went in 69, they collected the camera and took parts of it back to Earth. And when they brought it back to Earth, there was still some bacteria. Not many, but some bacteria had survived being on the moon for 2 years. I find this shocking. This room may have heard. How many people have heard of this? Okay. This is just shocking to me. If you know any biology, you know this makes no sense. This is what this means is they survived the launch. I mean, that's not that bad. They survived space vacuum. It means they didn't need air or oxygen. Survived space vacuum. 3 years of horrible radiation exposure, right? Because no atmosphere. Deep freeze at an average temperature of only 3 degrees above absolute zero, and I think that means Kelvin. That's a scary low temperature. No nutrients, no water, no energy source except for a few photons coming down. And they survived 3 years. This is getting towards, a few of you blurted out something about, well, wouldn't there be another way to get carbon if you lasted longer? Yeah, I think there probably would, and there's an incredible creativity that might be able to take some use to that carbon. Okay, so I've kind of gone through a history of how this reasoning works very well, thinking things are tuned if we assume life is a certain way. But then nature often pulls a different way to do life, which messes with those assumptions, or those conclusions. All right, I've gone through literature and history. Let me go through some language. These are quotes out of some books on the Anthropic Principle. I also have to say, I'm biased in that I'm trying to make an interesting talk by having confrontational and saying this is a bad thing. I am still intrigued, I have to admit. There is something intriguing that something does seem tuned, but it's hard to really grasp onto what. But these are words that's used a lot. And I've got these copies out of the books I've read. I started reading these as soon as David said, yeah, I think it'd be good if we gave a talk on this. So I had to start reading them. Delicately dependent. The fine-tuning is delicately dependent. Slightly different is a good one. There's often the phrase, if the value of the strong force had been slightly different. It's not given as a number. It's given the word slightly. Or very slightly stronger. Wildly improbable numerical add. You can read them. You've already read them. I did some stats. This is a fun thing about having access to Amazon or Google Books. You can then do searches and look for in a whole book how many words are in it, just with regular access. You don't need the fancy access. And slightly definitely wins out. It's used 14 times in Davies' book, The Excellent. It's used 20 times in Barrow's Constants of Nature. Just that adverb, adjective or adverb, oh dear, slightly. Okay, let's look at slightly then and look at some of this language. One of the slightlys is the 1 part in 10 to the 15th for gravity. Remember that? That was a New Scientist article. If gravity had been, and I agree, 1 part in 10 to the 15th, that means 0.00000, 15 zeros and a 1 difference in the value of gravity. That does seem like a slight difference. Could I have you quickly just stand up? You don't have to, but you're actually, I'm very impressed. If I were on my campus giving a seminar, I think maybe 3 people might. Wow, this is great. Okay, what you've just done by standing up is make your gravitational force that you're experiencing much, much stronger than 1 part in 10 to the 15th. Okay, sit down. Thank you. This is a fun little general physics calculation. By standing up, you have changed your distance from the center of the Earth by 1 meter about, by standing up. You can go and put in, if I weigh 100 kilograms, and that's either flattering or insulting, depending on who you are when you stood up. I can calculate what is the difference when I was sitting down, call that force 1, and then when I stood up, force 2. Just plug into Newton's law, force difference. And what you'll get is that difference shows up in the 7th decimal place. So you actually are experiencing a different force of gravity, 1 part in 10 to the 7th. Nothing bizarre happened. You didn't fall over, you didn't stop existing, you didn't become not intelligent. So obviously when there's this claim 1 part in 10 to the 15th, it isn't actually talking about what we may think it's talking about. Now actually I was talking with David before on his gravity simulations. That 1 part in 10 to the 15th, as I understand it, comes from some pretty detailed arguments about what it would have had to be right at the inflation time, because if something blows up really fast in an inflation, a little 10 to the 15th, 1 over 10 to the 15th, can turn into exponentially larger, and that can then get amplified. So I think it's at that level of reasoning, but that's not usually the one people think of when they think of this finely tuned. That's kind of a sophisticated reasoning with the inflation scenario. Oh yeah?
With this, were they not talking about, doesn't G stay constant, but in this situation doesn't R do the changing?
No, you're right. All I was, yeah, exactly. G does stay constant. What I was doing is just illustrating, it's a really good point. I was doing a bait and switch here. I could do G, M1, M2, all over R squared. Now if I had a nice little meter I could dial it by 1 part in 10 to the 7th. But I don't have a meter that can do that. But I can simulate that. I can change that force by just changing R by a certain amount. The R you'd have to change by isn't much. But you're exactly right. I was simulating how it would affect force of gravity to have G different. And it obviously doesn't affect things at a terrestrial level, was my point. Okay. Are there any other questions? Even in physics today, not new scientists I can forgive doing that hyperbole. This was a good article on how we actually get the isotopes in the cosmos, and it was really good. It was in Physics Today a few months ago, but it comes right out and admits some fun ideas that we don't actually know how we get a lot of the heavy elements. We have models, and that was kind of like that model I showed you, the nice PP reactions, and they work really well. But if you actually try to verify some of these cross sections and what are the reactions in a laboratory, it's very hard to predict what's really happening. And this is admitted in the article. Right about here, before I cut it off, it says, but we still do not know where the process, there's an R process and an S process, slow reactions, fast reactions to create heavier elements from lighter elements. We still do not know where the R process takes place and what exactly the reaction sequence is that builds up these heavier elements. Now this isn't me saying, see, science doesn't know it. So I'm just letting you know, even scientists will admit when you push them, yeah, this is our model for the reaction sequence. So if you're going to say things are incredibly fine-tuned, but that's given that my model is what I think the model is. There's a little grain of salt. This was that one I went through before, that the carbon nucleus has to be tuned And this is the one that sent two of you getting all upset and good, which is good. It got two of you. You're in a good company. It got Stephen Weinberg, Nobel Prize. He got a little upset about this too. Wait a minute, is this really showing that there's some reasoning? Is that resonance really tuned to have to be just that value of carbon to give me the reactions in stars? He went back and did an analysis, Stephen Weinberg, and he showed there's very little fine tuning. You can have a slop in the nuclear energy levels up to 20% of that value that Hoyle predicted and still get lots of carbon. It doesn't have to be right at that 13.65. And so he has in his traditional, acerbic tone, the fine tuning isn't all that fine in this case or something like that. Okay. Let's move to the subject of chemistry then. Since we're talking about carbon, might as well go to chemistry. This was another one that Weinberg looked at, and actually I'm going to go kind of quickly through it. Our fixation with carbon, of course, is because we know we're carbon-based organisms. It's because, of course, the DNA and then a protein. Protein is a carbon polypeptide. So carbon is important. Weinberg went and analyzed many of the processes in a star, and he was even able to come up with models where you don't start with hydrogen going to helium and then helium to carbon. He showed you could change parameters. If you change more than one, say change G and change the strong force, you can get a whole different reaction sequence where you actually burn helium first, and then hydrogen, and then go to carbon, and it uses a PEP instead of a PP. So it just takes you can think of ways around this way that it could have been done. Now here's one, move to mathematics as a subject area. And this is the one kind of dear to my heart as a physicist. Most physics teachers I know, and I'm sure David, how many people have David in a class? Dr. Garrison, sorry. And this may not be true, you may be, but a lot of times your physics professor can't even remember these constants, right? Or you set them equal to 1, right? Physicists actually aren't usually that excited about the constants. It's more the laws itself, that they have this mathematical harmony. That seems the thing that catches our attention. And so this is under the heading of mathematics. A lot of times you can explain away an apparent tuning of parameters by just getting a better model of it. As an example, I had that whole example about the mass of the proton and the mass of the neutron and how they're tuned. Well, you've all probably heard of quarks, right? A proton is just 3 quarks, and a neutron is just 3 quarks. So really when I'm talking about that proton, it's up, up, down quark, and the neutron is up, down, down quark. And so if you're saying, yeah, those mass of proton, no. This translates in a better model into, it's the mass tuning of the D quark or down quark that has to be tuned. So you can see as soon as you change your model, you also are changing the thing that you think is tuned. And these masses, of course, are not in a pure sense. This is, I have to get into maybe too much physics, but the strong force, it relates to a whole different coupling, which is the strong force, so that parameter enters in addition to the mass. Maybe an easier one, and I don't really understand this at any level further than that, is Newton's law itself, which I wish I wouldn't keep erasing, because it's a great, I'm going to keep referring to it.
I think the board extends further the other way.
Really?
No, other way.
Wow, that's great. All right. Yeah, maybe I'll write it here and then I'll never have to erase it. Fg, m1, m2, all over r squared. Coulombs law is similar, where you have a k and it's 2 charges, q1, q2 over r squared, and that would be the electric force. There was some work done, and many experiments were done. I don't know if it was Faraday or who. Why is it 2? Why not 2.11? Why not 2.8? These kind of things. It seems like it's fine-tuned to be 2. Because you can show if it's not 2, you get some bad consequences. But this is just a mathematical thing. You could turn this around and say, no, the reason it's 2, it's the only thing that makes a logically consistent planetary orbit. If you make it 2.15 and you run a simulation, now I haven't done this. I do know you have to have it exactly 2 to have your orbits repeat. Otherwise you get a spirograph kind of thing, I think, right? So if you had different than exactly 2, you can't have even what we talk about as a nice closed, energy-preserving periodic orbit. So at this level, it's mathematical consistency that's forcing it to 2. Yeah.
Also with the gravity force, since Newton's law here is just an approximation of Einstein's general relativity, then it could be that it just shows up in that form just because
the approximation
what works out, and it's not exact like that. But the Coulombs Law, you could also say is like an approximation coming from the quantum.
Well, that's true.
law
That's a
in
gauge
this case.
symmetry. It's some high level, you're right, gauge symmetry, Maxwell, Gauss's law, and that's why it's this. Yeah, exactly. So if you just change your model, it's obvious why they have this form. They have to have this form because of Gauss's law or Einstein's equations. Yeah, that's a good point. And so if you're going to say, in a sense, it could retard science if you say, boy, I love how this is tuned. I'm just going to sit and be amazed at how it's tuned, because you're going to miss perhaps the deep reason of why there is that tuning, and it may be due to mathematical reasons. Like inertial and gravitational mass, that's another. Are they tuned? And you realize, no, the beauty is you have a deeper model. The reason they're tuned is they're the same thing, and that's very deep. They're not 2 different things. Here's another. Isn't it beautiful how all these 114 elements are all tuned to have just the masses to let us do chemistry? We of course know, there's a reason, there's a model behind this. There are not 114 different things. There are, 3 things. Up quarks, down quarks, and electrons. That's an incredible reduction of tunings, going from there's 114 things tuned, but now I'll change to the atomic theory and the quark theory, and now there's 3 things tuned. Okay. So the point is the tunings are dependent on, and the constants are dependent on what your model is in the first place. Another example I like, when you do the Maxwell unification, when you unify theories, you have this happen. If I do Maxwell's equations and I unify electricity and magnetism, well, in the electric force, you have a constant 1 over 4 pi epsilon 0. Magnetism has a similar constant called mu 0. So there's an epsilon and a mu, which describe the strengths of gravity and the strengths of magnetism. Well, then Maxwell comes along and says, those are not actually independent. They're related to the speed of light. So now they're not actually independent things. Once you do the unification, in a similar sense, then electricity and magnetism, you may have heard, were unified, and it was Weinberg, with the weak interaction, which is radioactive decay. That's the electroweak. That unification is interesting, because the mass of the electron then becomes related to some, now maybe, you may say this is even worse, but mass of the electron can then be written in terms of other constants in the weak force. A G and an omega. Now I pause because to me that kind of looks even worse, like the situation. But anyway, the point is the constants are now in terms of something different. The electron mass is not a constant. It's related to something that happened in symmetry breaking in the early universe. All right, I'll try to go in about 5 minutes, and I'm going to try to go to the 2 that are most important to me. And these are from biology. These last 2 critiques, at least inspired by biology. And I'm going to skip over one of them and get right to, and I think this is an interesting question to ask. Why don't biologists have an anthropic principle? Why is it physicists who have an anthropic principle? I think that bears some pondering a little bit. And I have a nasty, I'm a physicist, so I don't mind the slant. And I think it's because physicists don't actually understand life. And so it's easy for them to say, I've got this model and this principle that shows why there's life, and anthropic. Biologists, because they understand life, are a little more humble at knowing that we don't really understand life. So for us to say, yes, I can start with H psi equals E psi and things are tuned just great to give me life, that assumes that you really could get from these equations, Maxwell or Newton or something, or Einstein, and somehow do a bunch of chalkboards, which would put everyone to sleep, and end up with, End up with, even I defy anyone, even in the advanced grad students here, start with H psi equals E psi, Schrodinger's equation, or Newton's laws and end up predicting, after a bunch of pencils and paper, even computer simulations, this structure. Of course, a pure physicist could not do it for several reasons. One is, a pure physicist doesn't know what the structure is, so of course you couldn't predict it. Now I'm setting that up as a joke, but it's a epistemological problem. If you don't know that something exists, you can't predict necessarily that it does. Now you may disagree that it's true. Except for simple things like cross-sections of reactions or dropping a ball. If I show you, this is the structure of a protein called cytochrome C. If I show you that structure, if you know it exists, then you can say, is it consistent with Maxwell's equations? Is it consistent with Newton's laws? Yes, and you can say whether it's consistent or not, but you can't start with those, I defy you to, with Maxwell's equations and derive this as a steady state solution or even a dynamic solution. All right, here's another reason life is interesting, and could it? These, you notice there's two. I don't know if you noticed there was two, or you thought you're seeing double because the talk's going too long. So. One of these is the cytochrome C. It's in your mitochondria and it helps make your energy. It's part of your metabolism, just like that thermophilic bacteria. Gobs of these in every cell. One of these is from a chimpanzee and one is from a human. Can you tell the difference? And I'll save you time, there is no difference. It's identical. I'm sure you've all heard, when you look at the gene sequences, there's 98% the same. That's what this translates into. It means there's proteins which are completely identical. Now, this is if you're going to say the constants of nature, and the anthropic principle in the designing is usually done in terms of intelligent life. And I actually don't know why that is, to be honest. But it is. It isn't just, it's tuned to make ants, or it's tuned to make bacteria. That would be the ant principle or something. It's not that. It is intelligent life or observers. What tuning are you doing in your theory that gives you this instead of that, when this and that are the same? You may say, well, you've chosen two things that are very close. All right, let me put up cytochrome C. Actually, I don't have the picture here. If you put up cytochrome C for a bacteria, it's different by only 2 locations in the entire protein. So what tuning was there in any constant of nature that gave you the one that's only different? There is no tuning, is the thing. Or I don't understand how there could be a tuning. The point is, when you get to the level of life, and this is hard for a physicist to admit, I have to admit, when you get to the level of life, it's no longer physics that's in charge. Those are not the parameters or the laws that are in charge of things. What are those principles? Biologists are humble enough to say, we really don't know what they are. I think they have to do a little with computer science. Here is an example of bacteria. Bacteria work on algorithms. And this is getting into my speculation part of things, but not that they work on it, but the speculation of why this anthropic and this tuning would be a nonsensical way of looking at things. Bacteria work on algorithms. You can get bacteria to swim. It's a simple machine, and it has an algorithm. If the concentration in one direction at time t1 is greater than at t, then tumble your propeller. If it's not, make your tumble time short. I don't have time to describe it. It's just a simple tumbling the rotor of a bacteria. It just has to measure concentration at 2 points. You can get them all swimming in one direction with an algorithm. Okay. Algorithms, are independent of architecture. You can run on a Mac, you could run on a windmill, you could run on Tinker Toy sets. In the old days, you could run on transistors. The algorithm is what gives you the motive behavior or something of your system. This is for calculating pi. The underlying architecture isn't important. When you look at biologists and do their work, this is why we physicists don't want to do biology, really. This is what biologists do. It's networks and algorithms of a cell. Do you see any carbon atoms here? No. They don't need to talk at the level of carbon atoms. This is a horrible one. This is why I'm still glad that I teach physics. I don't have to teach any biology. But the point, you don't have to do carbon. In a complex system, it's almost at that level it doesn't need carbon. So if you think there's a designer, and I think it's fine if you do think, it's probably a very sane and healthy way to go through things, actually. If you think there's some designer, do you really think the designer needs to have carbon to make all these strange network diagrams work? Or do you think, let's say stars would have gone different, I changed the constants in some way so that I never get carbon, I only get, and of course we don't know what it is. because we don't know what that universe is. Are you saying that couldn't be used to create whatever a designer wanted to create, especially if you think the designer is all powerful or something? Well, of course, I think you could take anything. You could take clay. You could take anything as your substrate. And I think since it's 8, I'll probably just stop. I had more pretty pictures of proteins and things. We'll just end with Candide. We only have one universe and one life form. This is a problem. We only know of life here, and so we assume it has to be carbon. But that's that Goldilocks fallacy. And this is, I'm talking to an audience too, which I think knows this, because you probably get astrobiology talks that great. It's naive to think it would have to be carbon. This would be like only having found one book. Some extraterrestrials only found one book, and they concluded, boy, every book must have a character called Pangloss, every book must be written in French, every one must be 60 pages. When of course we know it's not the words in the book as atoms that are important, it's the things that go into the book, the story, and all of that. Okay, thank you very much.
Okay, questions for our speaker?
Yeah.
You flashed a slide, it looked like the geometry of space-time.
That's right.
Could you go back and discuss that?
Sure. This was another example of tuning, and I may defer to you or David, but another kind of tuning, there's a critical density, how much matter happened to be in the universe. There could have been any amount of matter at the Big Bang. There could have just been 4 protons, or 4 quarks, or there could have been a huge number. There was a certain number, that happened, a certain amount of energy density, or matter density. It turns out if that was too large, the universe greater than the critical density, which we call 1, the universe would have crunched right back down and became a closed universe. Or if that density was less, it would keep expanding forever. It seems to be, the density, though, that was created at the Big Bang seems to be at just the level so that we have perfectly flat space. Now, astrophysicists can say this a lot better. Inflation throws other loopholes in here. You could say, though, inflation is an example where it explains away that tuning. It isn't that it was critically chosen the mass so that space is flat. Inflation says that's not a tuning at all. It's that inflation happened and it's stretched. Any shape you start with, this positive or this negative curvature will get stretched due to inflation into flat, and that's why it's flat. It's not tuned to be flat. So that's what that slide was for. It was another example of tuning, where if you just change your model, i.e. to inflation, it can get rid of the mysterious tuning because the model accounts for it. Did that answer the question at all?
Yeah, I just want to know how you use this one.
Yeah, okay, because it's such a pretty slide. You must be like a math geometry brain. That was a slide that made you go. Yeah, Alan?
Yeah, I'm just going to think that, and even this is an example of the neutron proton purposes also. Almost as if you're saying, okay, the actual apparent anthropic principle is not there because this is not really the issue is actually something else. But the anthropic principle could equally apply to something else. And you kind of admitted that in the context of the proton and neutron quark.
Yeah, the quark one, right?
Right. And here also you're saying, well, this is not really a problem because inflation gets rid of the problem, but is the inflation itself anthropic?
Right.
So I guess I'm really saying, okay, if it's not the anthropic principle at work, then what is it?
You can push it. I think you can argue still anthropically into these. Even inflation has, those of you know, inflation takes a lot of other tunings. The scalar field has to have this certain spectrum of density perturbations, and if that's off, then again, you'll get horrible expansions that don't work out. So yeah, that does actually have tunings. So you turn that the other way. My personal thing is the constants is what bugs me. To get obsessed with the constants, to me, what is the thing? It's the fact that, here's a way to put it. It doesn't matter what the value of G is if there isn't a law of gravity to start with. So to me, this is what makes me think, if anything, anthropically. The fact that there's law, and this is the Greek word for it, logos. And those of you who know your biblical references, I don't have to say anymore. Logos or law or purport, that to me, that's the big thing. The constants, that's like what color is your shirt? I don't think that would be a stumbling block to an anthropically oriented universe. This is the big thing, that there is law at all is the stunning one to me. Why would that be? Okay. Yeah. Yes.
Since unification is such a big deal in physics now, is the idea of the multiple bubble universes, like lots of them, 10 to some big number. And is that just a way to get the ideas of quantum mechanics into cosmology? Because every wave function is just a distribution of an infinite number of outcomes of something. So the bubble universe is just a way to say, oh, here's an infinite number of outcomes of this distribution, and we're in one of them. We're just a point in the distribution.
Yeah, this,
Because
I drew this as very schematic, the multiverse, just giving the impression that if you just went far enough light years in that direction, the value of G would be different. But there's another model you're kind of saying, no, this is happening in a Hilbert space, and that's where the multiverse is.
oh no, maybe the real space of all those universes, all nearby each other, and you can go, billion, trillion light years that way to the other universe, and there's some weird other life over there. And it's just another point in the overall wave function of the multiverse. See that? We're just a point in the wave function of the multiverse, but there's all these other points in the wave function of the multiverse too.
Yeah, I don't know how to respond.
I think.
I'm not a multiverse. I'm kind of multiverse agnostic. I don't.
Okay.
To me, it's
that was my question. Is why are the cosmologists doing this just to get quantum mechanics into
I'm
cosmology?
going to defer to David. What do you think or anyone, the motive?
Because they want to unify it so bad, so let's put it in there through the back door.
Yeah, I think the whole idea of that was just to try to find a way to explain why we get the laws we get. And I've never been a big believer in multiverse theory, so it seems like to me that's basically just how do you get from having these laws and they're set up in this way, and how do you explain it? And it just seemed like, well, you just try all different things and eventually you find what works, and then what works happens. And I think that's just basically the way they came about it.
Yeah, it's taking it literally as if they actually exist.
Yeah, because the truth is, once you get outside of the observable universe, which is about 3.7 billion light years, there's no way the information from outside of there could technically have gotten to us yet, because there just hasn't been enough time.
Yeah.
And so you really don't know what's out there. You don't know what the measurements are of the fundamental constants. You don't know if you go through a wormhole and there's a different horizon there, that you won't end up in somewhere else which has completely different fundamental constants. It's like there's no way to know what's going out there. So if there's no way to know what's going out there, you can put whatever you want in there.
Yeah.
And that's kind of one of the secrets in physics is that as soon as when we did black hole simulations, once you get inside the event horizon, you don't get any information out. So what happens is when you're doing your simulation, you get inside the event horizon and chop off your simulation there, so it doesn't actually go to a singularity or a point. And the physics is 100% accurate because, it could be anything in it. It could be a garbage dump, it could be a beach, a nuclear reactor, whatever.
Hey, when you're doing all that, are you doing science?
What, you mean when you're speculating about what's going on outside of your model?
Are you just clever thinking in mathematics, or are you doing science?
When you're actually looking at within your model and within what you can observe and you can test and you can do some kind of measurement, at that point you're doing science. When you get beyond what you can really observe to the point where anything could physically be going on in there and you have no way of finding out, then it's kind of debatable about whether or not you call that science. Like if you talk to a string theorist, what they do when they're talking about string theory, the whole idea is based on these multi-dimensional tiny strings that are vibrating at different frequencies in these different dimensions. And there is no way you can ever experimentally test that. You could spend all the Earth's money on a super collider, you could build whatever you want. There's nothing within the laws of physics that will ever let you test to see if that's really true. So you can debate, is that science if you can't test it? And one definition of science is that it has to be testable.
That's right.
It doesn't mean that testing it is unlikely. I mean, I could design a theory which involves cosmic rays.
And it may take you 100 or maybe even 1,000 years to collect enough data to test my theory, but it's testable. But I'm talking about where you get beyond that and you can't even test it. Then
Not even in principle, right?
not even in principle.
That's true. If it's outside your event horizon or your Hubble rate, not even in principle, you can't make the light go faster to
Yeah.
observe that other universe.
And that's the flaw with multiverse also, you're not testing it.
Right.
It's nice that maybe a catch-all or a way of
Yeah.
getting around problems, but there's no way to confirm it.
I also wonder in if you're going to say the law of the constants can be different, what about other things? Like, does logic still apply? I mean, you can really start to go down, there's the principle of excluded middle, like what thing is varied? And you get into a hole. Okay.
Yeah. Other questions? All right, let's thank our speaker. And I want to remind everybody, next week's lecture, we're going to have Ann Riley, who works here at UHCL, and she's going to be giving a talk about giant magnetoresistance from the laboratory to the hard drive. And it should be very interesting. So, I'll see you guys. I'll see you guys. I'll see you guys. I'll see you guys.